Hello there, everyone. Hope you're having a fantastic day wherever you are in the world. Thank you for your kind, good vibrations and prayers for my son's healing. It was quite scary and serious, yes. Okay, just a question. Who do you think invented the steam engine? Most people would say James Watt. He was he was the one that's what we grew up knowing. But no, it's not true. No. Okay, history of the steam engine. The first recorded rudimentary steam engine was the aeropile, described by Heron of Alexandria in the 1st century by Rome, Egypt. Several steam-powered devices were later experimented or proposed, such as, I cannot say that, don't even want to butcher it and try, steam jack. So it's a machine that roasts meat. Look. Steam turbine, like, your jet engines have similar turbines. In the 16th century, Ottoman Egypt, and Thomas Savery's steam pump. In the 17th century, England, in 1712, Thomas Newcomb's atmospheric engine became the first commercially successful engine using the principle of the piston and cylinder, which was the fundamental type of steam engine used until the 20th century. Steam engine was used to pump water out of coal mines. It was also used to pump sewage. It was also used to pump sewage and pump water around, villages for people. During the Industrial Revolution, steam engines started to replace water and wind power and eventually become the dominant source of power in the late 19th century, and remaining so to the early decades of the 20th century, when a more efficient steam turbine and industrial combustion engine resulted in the rapid replacement of steam engines. The steam turbine has been the most common method by which electrical power generators are given. Investigations have been made into the practicalities of reviving a reciprocating system engine as the basis of a new wave of advanced steam technology. And some steam-powered vehicles can go really fast. Early uses of steam power. The earliest known rudimentary steam engine was an reaction steam turbine. An aeropile is described by a mathematician and engineer named Heron of Alexandria. Heron, in the 1st century of Roman Egypt, as recorded in his manuscript Spiritella sul Pneumatic, steam ejected tangibly from nozzles caused by a pivoted valve to rotate. Its thermal efficiency was low. This suggests that the conversion of steam pressure into mechanical movement was known in Roman Egypt in the 1st century. Heron also devised a machine that used air heated in an altar fire to disperse a quantity of water from a closed vessel. The weight of the water was made to pull a hidden rope to operate temple doors. Some historians have conflated the two inventions to assert incorrectly that the aeropile was capable of useful work. According to William of Malmesbury in 1125, Reims was home to the church that had an organ powered by air escaping from compression by heated water, apparently designed and constructed by Professor Grubertus. Sorry for saying this wrong. Among the papers of the Leonardo da Vinci, dating to the late 15th century, is the design for steam-powered cannon called, don't even want to try and say that, sorry, which works by the sudden influx of hot water into seal a red-hot cannon. Rudimentary impact steam turbine was described in 1551 by this guy, a philosopher, astronomer, and engineer in the 16th century Ottoman Egypt, who described a method for rotating a spit by means of a jet steam playing on rotary vanes around the periphery of a wheel. Similar device for rotating a spit was also later described by John Wilkes in 1648. These devices were called mills, but are known as steam jacks. Mills were also used, to produce cotton and clothing and flour, food. Another similarly rudimentary system turbine is shown by an Italian engineer who, in 1629, for turning cylindrical escapement of a device that ultimately lifted and let fall a pair of pistols working in mortars. The steam flow of these easy steam turbines, however, was not concentrated, and most of its energy was dissipated in all directions. This would have led to great waste of energy, so that they were never seriously considered for industrial use. 1605, French mathematician Florence Revel, in his treatise on artillery, wrote, on a discovery that water, if confined in a bomb shell and heated, would explode the shells. 1606, the Spaniard demonstrated and was granted a patent for a steam-powered water pump. The pump was successfully used to drain the inundated mines of this place in Spain. Discoveries that, when brought together by Thomas Newcomen in 1712, resulted in the steam engines were concept of vacuum, i.e. a reduction of pressure barrel ambient, concept of pressure, techniques of creating a vacuum, the means of generating steam, the piston and the cylinder. 1643, this guy conducted experiments on a suction lift water pumps to test their limits, which was about 32 feet. Atmospheric pressure is 32.9 feet or 10.3 meters. Vapor pressure of water lowers theoretically lift height. He devised an experiment using a tube filled with mercury. And invented a bowl of mercury, the barometer, and observed an empty space above the column of mercury which he theorized contained nothing, that is, a vacuum. Influenced by this guy, this other guy invented a vacuum pump by modifying an air pump used by pressuring an air gun. Grickel put on a demonstration in 1654 in Magdeburg, Germany, where he was mayor. 2 copper hemispheres were fitted together and the air was pumped out. Weights strapped to the hemispheres could not pull them apart until the air valve was opened. The experiment was repeated in 1656 using 2 teams of each 8 horses each, which could not separate the main dome spheres. Very interesting. Gaspar Scott was the first to describe the hemisphere experiment in his Mechanica Hydropneumatica. After reading Scott's book, Robert Boyle built an approved vacuum pump and conducted related experiments. Dennis Papin became interested in using the vacuum to generate motor power while working with Christian Huygens and Godfrey Libaz in Paris in 1663. Papin worked for Robert Boyle in 1676 to 1679, publishing an account of his work in the Continuation of New Experiments, 1680. Continuation of New Experiment. And gave a presentation to the Royal Society in 1689. From 1619 on, Papin began experiments with a piston to produce steam power with steam. Building model steam engines, he experimented with atmospheric and pressure steam engines, publishing his results in 1707. 1663, Emma Somerset and 2nd Marquess of Worcester published a book of 100 inventions which he described a method for raising water between floors employing a similar principle that of a coffee percolator. His system was the first to separate the boiler, a heated cannon barrel, from pumping action. Water was admitted into a reinforced barrel from a cistern, then the valve was opened to emit the steam from a separate boiler. Pressure built over the top of the water, driving it up a pipe. He installed a steam-powered device on the wall of the Great Tower at Raglan Castle to supply water through the tower. The grooves in the wall, where the engine was installed, were still to be seen in the 19th century. However, no one was prepared to risk money for such a revolutionary concept, and without backers the machine remained undeveloped. So these huge castles, they didn't have people carrying buckets non-stop by the sound of it. Samuel Morland, a mathematician and inventor who worked on pumps, left notes on the Vauxhall Ordnance Office on steam pump design that Thomas Savery read. In 1698, Savery built a steam pump called the Miner's Friend, employed both vacuum and pressure. These were used for lower horsepower service for a number of years. Thomas Newcomen was a merchant who dealt in cast iron goods. Newcomen's engine was based on a piston and cylinder design proposed by Papin. In Newcomen's engine, steam was condensed by water, sprayed inside the cylinder, causing atmospheric pressure to move the piston. Newcomen's first engine installed for pumping in a mine in 1712 at Dudley Castle in Staffordshire. Dennis Papin, 22nd of August 1647, 1712, French physicist, mathematician and inventor, best known for his pioneering invention of the steam digester, the forerunner of the pressure cooker. In the mid-1670s, Papin collaborated with the Dutch physicist Christian Huygens on an engine which drove out the air from a cylinder by exploding gunpowder inside it, releasing the incompleteness of the vacuum produced by this means. And moving to England in 1680, Papin devised a version of the same cylinder that obtained a more complete vacuum from boiling water and then allowed the steam to condense. In this way, he was able to raise weights by attaching the end of the piston to a rope, passing over a pulley. As a demonstration model, the system worked, but in order to repeat the process, the whole apparatus had to be dismantled and reassembled. Kaplan quickly saw that to make an automatic cycle, the steam would have to be generated separately in a boiler. However, he did not take the project further. Papin also designed a paddle boat driven by a jet playing on a mill wheel. In a combination of Den and Savory's concepts, he is also credited with a number of significant devices such as the safety valve. Papin's years of research into the problems of harnessing steam also played a key part in the development of first successful industrial engines that soon followed his death. Savory steam pump. The first steam engine to be applied industrially was the fire engine, or a miner's friend, designed by Thomas Savory in 1698. This was a pistonless steam pump similar to the one developed by Worcester. Savory made two key contributions that greatly improved the practicality of design. First, in order to allow the water supply to be placed in below the engine, he used condensed steam to produce a partial vacuum in the pumping reservoir, the barrel in Worcester's example, and using that to pull the water upwards. Secondly, in order to rapidly cool the steam to produce the vacuum, he ran cold water over the reservoir. Operation required several valves. When the reservoir was empty at the start of the cycle, the valve was opened to admit steam, the valve was closed to seal the reservoir, and the cooling water valve turned on to condense the steam and create a partial vacuum. The supply valve was open, pulling water upward to the reservoir, and a typical engine could pull up 20 feet. This was closed and steam valve reopened, building pressure over the water and pumping it forward as in the Worcester design. The cycle essentially doubled the distance that water could be pumped for every given pressure of steam, and production examples raised water above 40 feet. Savory's engine solved a problem that had only recently become a serious one, raising water out of the mines in southern England as they reached greater depths. Savory's engine was somewhat less efficient than Newcomb's, but this was compensated for by the fact that the separate pump was used by Newcomb engine was inefficient, giving the two engines roughly the same efficiency for 6 million feet of pounds per bushel of coal, less than 1%. Nor was the Savory engine very safe because part of its cycle required steam under pressure supplied by a boiler, and given the technology for the period of the pressure vessel could not be made strong enough, so was prone to explosion. The explosion of one of his pumps at Broadwaters near Winstonbury about 1705 probably marks the end of attempts to exploit his invention. The Savory engine was less expensive than Newcomb's, and was produced smaller sizes. Some builders were manufacturing improved versions of the Savory engine until late 18th century. Bento de Moura, Portugal, introduced an ingenious improvement of Savory's construction to render it capable of working itself, as described by John Smeaton, The Philosophical Translations, published in 1751. So the atmospheric condensation engines, Newcomen's atmospheric engine. It was Thomas Newcomen with his atmospheric engine of 1712 who can be said to have brought together the most essential elements established by Papin in order to develop the first practical steam engine for which there could be a commercial demand. This took shape of a reciprocating beam engine installed at the surface level, driving a succession of pumps at one end of the beam. The engine, attached by chains from the other end of the beam, worked on atmospheric or vacuum principle. Newcomb's design used some elements of early concepts like the Savory's design's Newcomen's engine used steam cooled with water to create a vacuum. Unlike Savory's pump, however, Newcomen's used the vacuum to pull on a piston instead of pulling on water directly. The upper end of the cylinder was open to the atmospheric pressure, and when the vacuum formed, the atmospheric pressure above the piston pushed it down into the cylinder. The piston was lubricated and sealed by a trickle of water from the same system that supplied the cooling water. Further, to improve the cooling effect, he sprayed water directly into the cylinder. The piston was attached by a chain to a large pivoted beam, and when the piston pulled the beam, the other side of the beam was pulled upward. The end was attached to the rod and pulled on the series of conventional pump handles in the mine. At the end of this power stroke, the steam valve was reopened, and the weight of the pump rods pulled the beam down, lifting the piston and drawing the steam into the cylinder again. Using the piston and the beam allowed Newcomb's engine to power pumps at different levels through the mine, as well as eliminating the need for any high-pressure steam. The entire system was isolated in a single building on the surface. Although inefficient and extremely heavy on coal, Compared to later engines, these engines raised far greater volumes of water from the greater depths that had previously been possible. Over 100 Newcomen's engines were installed around England by 1735. It's estimated that as many as 2,000 were in operation by 1800, including Watt versions. Now, I'm not 100% sure if this is the same sort of, situation setup, but to me it seems to look this way. So the Victorian Engine House, 1865. I just wanted to show you the beautiful machine. It's just marvellous. It's been restored. Okay, so this is at Crossness. I just want to show you quickly how big this is. I'm sure it probably wasn't as big as this for the mines, but it's just, like the intricate work on it and everything is just beautiful. The Alexandra engine. And this goes down, I think it's 40 feet down below, I think it goes. So it's the top with the piston valve, the bearing engine. Starting the engine. I just love the sound of the old engines, the steam engines, the knock in the way everything just moves. Here we go with the big wheel. It take a while to get going, these old girls, but once they get going, they go. Get the water up and the fire going, they'll go as never stop. Beautiful machine. One of the 2 position marks at 108. So, yeah, this goes right down. It's massive. Main steam valve. It would have been a hot place to be in, but the computer's a bit bad at the moment, sorry. So, the Alexandra. So this valve gear is older than what we've been told. This technology is way older than what beautiful metalworking and the casting and everything that's been put into it. It's just unreal. Rocking beam 43 feet wide. So I have a playlist of steam saved in my playlist. John Smeaton made numerous improvements to the Newcomen engine, notably the seals, and by improving these was able to almost triple their efficiency. He also preferred the use of wheels instead of beams for transferring power from the cylinder, which made his engines more compact. Smeaton was the first to develop a rigorous theory of steam engine design and operation. He worked backwards from the intended role to calculate the amount of power that would be needed for the task, the size, the speed of the cylinder that would provide it, the size of the boiler needed to feed it, and the amount of fuel it would consume. These were developed numerically after studying dozens of Newcomen's engines in Cornwall and Newcastle and building an experimental engine of his own in his home in Osthorpe in 1770. By the time the Watt engine was introduced only a few years later, Smeaton had built dozens of ever larger engines into the 100 horsepower range. Watt's separate condenser, while we're working at the University of Glasgow, an instrument maker and a repairman in 1759, James Watt, the man we all were told invented the steam engine, was introduced to the power of steam by Professor John Robson. Fascinated, Watt took to reading everything he could on the subject and independently developed the concept of latent heat. Only recently published by Joseph Blank at the same university, when Watt learned that the university owned a small working model of the Newcomen engine, he pressured to have it pressed to return from London, where it was being unsuccessfully repaired. Watt repaired the machine, but found it was barely functional even when it was fully repaired. Okay. So over 100 installed by 1735. Estimated as many as 2,000 were in operation. After working with the design, what concluded that 80% of the steam used by the engine was wasted. Instead of providing motion force, it was instead being used to heat the cylinder in the new Newcomen design. Every power stroke was started with a spray of cold water, which not only condensed the steam but also cooled the wells of the cylinder. This heat had to be replaced before the cylinder would accept steam again. In the Newcomen engine, the heat was supplied only by steam, so when the steam valve was open again, the vast majority of the condensed on the cold walls as soon as it was emitted into the cylinder. It took a considerable amount of time and steam before the cylinder warmed back up and the steam started to fill up again. What solved the problem of the water spray? By removing the cold water to a different cylinder placed beside the power cylinder. When in the induction stroke was completed, the valve was opened between the two, and any steam that entered the cylinder would condense inside this cold cylinder. This would create a vacuum that would pull more steam into the cylinder, and so on until the steam was mostly condensed. The valve was then closed, and the operation of the main cylinder continued as it would on a conventional Newcomen engine. As the power cylinder remained at operational temperature throughout, the system was ready for another stroke as soon as the piston was pulled back up the top. Maintaining the temperature was jacket around the cylinder where the steam was emitted, what produced a working model in 1765. Convinced that this was a great advance, Watt entered into partnerships to provide venture capital while he worked on the design. Not content with a single improvement, Watt worked tirelessly on a series of other improvements to practically every part of the engine. Watt further improved the system by adding small vacuum pumps to pull the steam out of the cylinder into the condenser, further improving cycle times. A more radical change from the Newcomen design was closing off the top of the cylinder and introducing a low pressure steam above the piston. Now the power was not due to the difference of atmosphere pressure in the vacuum, but the pressure of the steam in the vacuum, a somewhat higher value. On the upward return stroke, the steam on top was transferred through a pipe to the underside of the piston, ready to be condensed for the downward stroke. Sealing off the piston on the Newcomen engine had been achieved by maintaining a small quantity of water on its upper side. This was no longer possible in the Watt engine due to the presence of the steam. Watt spent considerable effort to find the seal that worked, eventually attained using a small mixture of tallow and oil. The piston rod also passed through a gland at the top of the cylinder cover seal in a similar way. The piston sealing problem was due to having no way to produce a sufficiently round cylinder. Watt tried having cylinders bored from cast iron, but they were too out of round. Watt was forced to use the hammered iron cylinder. The following quotation is from Rowe, 1916. When John Smeaton first saw the engine, he reported to the Society of Engineers that neither the tools nor the workmen existed. Who can manufacture such complex machine without sufficient precision? Watt finally considered the design good enough to be released in 1774, and the Watt engine was released to the market. As portions of the design could easily be fitted to the new existing Newcomen engines, there was no need to build entirely new engines at the mines. Instead, Watt and his business partner, Matthew Bolton, licensed the improvements to the engine operators, charging them a portion of money that they would save them reduce fuel costs. This design was widely successful, and the Bolton and Watt Company was formed to license the design to help new manufacturers build engines. The two would later open the Soho foundry to produce engines of their own. In 1774, John Wilkinson invented a boring machine with a shaft holding the boring tool supported on both ends, extending through the cylinder, unlike then used cantilever borers. With this machine, he was able to successfully bore the cylinder for Bolton and Watt's first commercial engine in 1776. Watt never ceased improving his designs. He's further improved operating speed, cycle speed, introduced governors, automatic valves, double-acting pistons, a variety of rotary power takeoffs, and many other improvements. Watt technology enabled the widespread of commercial use in stationary steam engines. Humphrey Gainsborough produced a model condensing steam engine in the 1760s, which he showed to Richard Lovell Edgeworth, a member of the Lunar Society. Gainsborough believed that Watt had used his ideas for the invention. However, James Watt was not a member of the Lunar Society at this period, and his many accounts explaining the succession of thought proceeding leading to the final design would tend to veil this story. Power was still limited by low pressure, the displacement of the cylinder, combustion and evaporation rates, condenser capacity. Maximum theoretical efficiency was limited by the relatively low temperature difference on either side of the piston. This meant that for the Watt engine to provide for a usable amount of power, the first production engines had to be very large and thus very expensive to build and install. Watt developed a double-acting engine in which steam drove pistons in both directions, thereby increasing the engine speed and efficiency. The double-acting principle also significantly increased the output of given physical size engine. Boulton and Watt developed a reciprocating engine into the rotative type. Unlike the Newcomen engine, Watt engine could operate smoothly enough to be connected to a drive shaft via the sun and planet gears to provide rotative power along with double-acting condensing cylinders. The other example was built as a demonstrator and was installed at Boulton's factory to work machines for lapping, polishing buttons, or simmer. For this reason, it was always known as a lap engine. In early steam engines, the piston is usually connected by a rod to balance them, rather than directly to a flywheel, and these engines are therefore known as beam engines. Early steam engines did not provide consistent enough speed for cylinder critical operations such as cotton spinning. To control the speed, the engine was used to pump water for the water wheel which powered the machinery. High-pressure engines. As the 18th century advanced, the call for high pressures, this was strongly resisted by Watt, who used them. Mobley, his patent gave him to prevent others from building high-pressure engines and using them in vehicles. He mistrusted the boiler technology of the day, the way they were constructed and the strength of the materials they used. The important advantages of high-pressure engines were they could be made much smaller than previously for given power output, and thus was potential for steam engines to be developed that they were small, powerful enough to propel themselves and other objects. As a result, steam power for transportation now became a practicality in the form of ships and land vehicles, which revolutionized cargo business, travel, and military strategy, and essentially every aspect of society. Because of their smaller size, they were much less expensive. They did not require significant quantities of condenser cooling needed by atmospheric engines. They could be designed to run at higher speeds, making them more suitable to power machinery. Disadvantages were that low pressure range, they were less efficient than condensing engines, especially if the steam was not used expensively, and they were more susceptible to boiler explosions. The main difference between high-pressure and low-pressure steam engines work is the source of the force that moves the pistons. In the engines of the Newcomen and Watt, it is condensation of the steam that creates the most of the pressure difference, causing atmospheric pressure, Newcomen, and low-pressure steam, seldom more than the 7 psi boiler pressure plus condenser volume, Watt, to move the piston. A high-pressure engine, most of the pressure difference is provided by a high-pressure steam from the boiler. The low-pressure side of the piston may be an atmospheric pressure or connected to the condenser pressure. Newcomen's indicator diagram, almost all below the atmospheric line, would see a revival nearly 200 years later with a low-pressure cylinder of triple expansion engines contributing to about 20% of the engine power, again completely below the atmospheric line. The first known advocate of strong steam was Jacob Lepaud. Sorry for saying that wrong. In his scheme for an engine that appeared in encyclopedic works from around 1725, various projects of steam-propelled boats and vehicles appeared throughout the century, one of the most promising being Nicholas Joseph Cognotz, who demonstrated his Faraday steam wagon in 1769. Whilst the working pressure used for this vehicle is unknown, the small size of the boiler gave insufficient steam production rate to allow the Faraday to advance more than a few hundred meters at a time before having to stop to raise the steam. Other projects and models were proposed, but as with William Murdoch's model of 1784, many were blocked by Boulton and Watt. They did not apply in the US, and in 1778 a steamboat built by John Flitch operated in regular commercial service along the Delaware River between Philadelphia, Pennsylvania, Burlington, New Jersey, carrying as many as 30 passengers. The boat could typically make 7 to 8 miles an hour and traveled more than 2,000 miles, 3,200 kilometers during its short length of service. The Fitch steamboat was not commercial success as the route was adequately covered by relatively good wagon roads. In 1802, William Smithington built a practical steamboat, and in 1807, Robert Fulton used a Watt steam engine to power the first commercially successful steamboat. Oliver Evans, in his turn, was in favour of the strong steam, which he applied to boat engines to stationary users. He was a pioneer of cylindrical boilers. However, Evans' boilers did suffer several serious boiler explosions, which tend to lead weight to Watt's qualms. He founded the Pittsburgh Steam Engine Company in 1811 in Pittsburgh, Pennsylvania. The company introduced high-pressure steam engines to the riverboat trade in the Mississippi watershed. The first high-pressure steam engine was invented in the 1800s by Richard. The importance of raising steam under pressure from thermodynamic standpoint is that it attains a higher temperature. Thus, any engine under pressure steam operates at a higher temperature. Pressure becomes differential than is possible with a low-pressure vacuum engine. The high-pressure engine thus becomes basis for most further development of reciprocating steam technology. Even so, around the year 1800, high pressure amounted to what today would be considered very low pressure, i.e. 40 to 50 psi. The point being that the high pressure engine in question was non-condensing, driven solely by the expansive power of steam, and once that steam had performed the work, it's usually exhausted at a higher than atmospheric pressure. The blast of the exhausting steam into the chimney could be exploited to create induced draft through the fire grate, and thus increase the rate of burning, hence creating more heat in the smaller furnace, at the expense of creating back pressure on the exhaust side of the piston. On the 1st of February 1804, at the Penydarren Ironworks in Merthyr Tydal in South Wales, the first propelled railway steam engine or steam locomotive built by Richard was demonstrated. Cornish engine and compounding. So that's it there. Pumping water from a mine. Around 1811, Richard was required to update a Watt pumping engine in order to adapt it to one of his new large cylindrical Cornish boilers. When he left for South America in 1816, his improvements were continued by William Sims in a parallel. Arthur Wolff developed a compound engine with 2 cylinders so that the steam expanded in a high-pressure cylinder before being released into a low-pressure one. Efficiency was further improved by Samuel Gross, who insulated the boiler, engine, and the pipes. Steam pressure above the piston was increased, eventually reaching 40 psi or even 50 psi, and has now provided much of the power for the downward stroke. At the same time, condensing was improved. This considerably raised efficiency, and further pumping engines on the Cornish system, often known as Cornish engines, continued to be built new throughout the 19th century. Older Watt engines were updated to conform. The takeoff of these Cornish improvements was slow in textile manufacturing areas where coal was cheap due to the higher capital cost of the engines and the greater wear that they suffered. The change only began in the 1830s, usually by compounding, though adding another high-pressure cylinder. Another limitation of the early steam engines was speed variability, which made them unstable for many textile applications, especially spinning. In order to obtain steady speeds, early steam-powered textile mills used a steam engine to pump water to a water wheel, which drove the machinery. Many of these engines were supplied worldwide, gave reliable and efficient service over a great many years, with greatly reduced coal consumption. Some of them are very large, and the type continued to be right down to the 1890s. The Crossness engine, Crossness steam engine, patented in 1849, was called the greatest improvement since James Watt. The Crossness engine had greatly improved speed control, better efficiency, making it suitable for all sorts of industrial applications. Crossness used separate ports for steam supply exhaust, which prevented the exhaust from cooling the passage used by hot steam. Crossness also used partially rotating valves that provided a quick action, helping them to reduce pressure losses. The valves themselves were also a source of reduction friction, especially compared to the side valve, which typically used 10% of the engine's power. Crossness used automatic variable cutoff. The valve gear controlled the engine speed by using a governor to vary the timing of the cutoff. This was partially partly responsible for the efficiency improvement in addition to the better speed control. The Porter-Allen engine, introduced in 1862, used advanced valve gear mechanism developed by Porter-Allen, a mechanic of exceptional ability, and was at first generally known as the Allen engine. The high-speed engine was a precision machine that was well-balanced, achievements made possible by advancements in machine tools and manufacturing technology. The high-speed engine ran at piston speeds from 3 to 5 times the speed of the ordinary engines. It also had a low-speed variability. The high-speed engine was very widely used in sawmills to power circular saws. Later it was used for electrical generation. The engine had several advantages. It could, in some cases, be directly coupled. If gears or belts and drums were used, they could be much smaller size. The engine itself was also small for the amount of power it developed. Potter greatly improved the fly ball governor by reducing the rotating weight and adding the weight around the shaft. This significantly improved the speed control. Potter's governor became the leading type by 1800. The efficiency of the Potter-Allen engine was good, but not equal to the Crossness engine. The Uniflow engine. Uniflow engine was the most efficient type. High-pressure engine was invented in 1911 and was used in ships, but was then displaced by steam turbines and later marine diesels. Okay, so that's that one. But, yeah, I'm not sure on some of these dates. So, I'll leave the link for that Steam video I showed you. But, I was researching into, all of the goings-on throughout the centuries.